Oh, definitely come in person. Oh my gosh, no. If you have the option to go to a conference, go in person. That's the whole point of conferences.
All right, everyone. Good afternoon. It is great to be back at CppCon. Thank you for choosing to spend your time here with me, and I hope that you find this talk worthwhile and insightful. My name is Pejman, and I'm going to talk about your favorite subject, refactoring. How do I know refactoring is your bread and butter? Because as software engineers, we spend 17 hours of our weekly working hours maintaining existing software. So for anyone who's been in this industry for a while, chances are that you either love refactoring and maintaining software, or you're unhappy at least half the time. But what do we mean by maintaining software? We could define it based on all the activities it involves, or we can put our business hats on and think of it as making way for new features and improvements. But I like to think of it as reacting to changes in the outside world. Now, the world that we have is complex. So just maintaining software is allowing us to tend to our software, just like a gardener tends to his garden. After all, software is much like a living organism. It is constantly evolving. We change software for a variety of reasons: to make it work better, faster, and more efficient, to make the code simpler, more readable, and easier to understand or change in the future. We make these changes with good intentions. Some changes are easy, like fixing a compiler warnings. And some are difficult, like large-scale refactors and migrations that take time to do. Like this Indiana Bell building here on the screen that was rotated in 1930 without ceasing operations to make room for a new city project. But regardless of their type, every change that we make to our software runs the risk of breaking it. Managing this risk is the art that makes our craft interesting. Whether it's renaming a function or upgrading a third-party dependency, it is always possible for something to go wrong sometimes. And to manage this risk, we need to gain confidence that our changes are safe. The time that it takes for us to get to this confidence directly determines our productivity and efficiency. But despite our best effort, it takes engineering teams 23 days to get to this confidence. The goal of this talk is to show that continuous regression testing can help us reduce this feedback cycle and address this problem. In the next hour, we are going to cover what continuous regression testing is, how a continuous regression testing looks like in practice, how to build one, and how to use it to identify all sorts of regressions, including changes in build time and runtime. Then we're going to take a step back and think about what it takes to build good quality software. And I hope that I can convince you that building high quality software efficiently requires a culture of safety that combines a variety of tools and methods to mitigate the risk of everyday code changes. And as you can tell, we're going to cover a lot, so I ask that you keep your questions for the end. A little about me. I am a staff software engineer at Aurora. Our mission is to deliver the benefits of self-driving technology safely, quickly, and broadly. Every year, 42,000 people in the US and 1.5 million people around the world are killed in traffic accidents. It's a pandemic, and it's something that we can fix. Now, at Aurora, we are building technology that provides an incredible opportunity to save lives, make our roads safer, and give more people access to mobility. We're always looking for great engineers, so if you like to work on the forefront of technology and for a noble cause, I hope that you consider joining us. At Aurora, I'm part of the Technology Foundations team, building tooling and infrastructure to improve developer experience and productivity. While most of our core technology is written in C++, my team and I help accelerate the development of our web applications by maintaining shared libraries and shared components, such as our build system toolchain. I have 8 years of experience in building and maintaining mission-critical software systems. I started my career at a cybersecurity company and then moved to Canon to build software for 3D visualization of MRI and CT scans. We had this sign in our lobby that read, "What we do matters," and it was true. We were literally saving lives. The image you see on the screen is a sample output of that software, showing a CT carotid angiogram dataset taken as part of the stroke workup process to find potential occlusions in head and neck blood vessels. Building this image is challenging work because medical imaging datasets are a set of 2D images taken at different space and time. It takes significant engineering work to construct this 3D model that users can interact with. Medical images conform to a DICOM standard that define how to store and retrieve information in each 2D image. This information includes image data and metadata. But this standard is very old, and because there is no enforcement mechanism, it is up to medical device manufacturers to decide how closely they want to follow this standard and populate the required tags. As a result, one may encounter real-world datasets in which required tags are missing or inconsistent across images. All of this is a source of complexity, and for a mission-critical medical software, this source of complexity is risk. To make things more difficult, our software needed to support medical datasets that were created decades ago, where the standard was different. Manufacturers were even less compliant to the standard, and the physical hardware used for taking images was more primitive, so it was resulting in non-equidistant 2D images. A medical software designed for use by surgeons and clinicians cannot afford dismissing these edge cases that may lead to measurement discrepancies that could be life-threatening. I share all of this to remind you that the real world is messy and complicated and imposes ever-changing constraints. And to meet those real-world constraints, our software is large and complex. Because of this complexity, any changes to the system runs the risk of breaking it in ways that we do not expect. The interdependencies between system components and implicit assumptions made by each are just too many to keep track of. This is why when building real-world software, it is often good practice to validate our assumptions. And instead of dismissing edge cases as unlikely, we embrace this mindset that anything that could go wrong will go wrong. Now, defensive programming is a reasonable software development methodology, but validating every assumption is just not practical. So if we truly believe that every code change can break our software, then how could we stay productive and find the courage and confidence to go and make frequent changes? It's by establishing a mechanism to receive fast and reliable feedback on the impact of each code change. In practice, this means implementing multiple tiers of testing, and from unit test and component test to system-level test, and scaling those tests to be exhaustive enough to yield a high degree of confidence in the overall behavior of our system. Most organizations attempt to implement this mechanism to a varying degree. For example, they run unit tests and integration tests as part of their CI. But in most cases, higher level tests are pushed out to the testing phase of the software development lifecycle, the outer loop in this diagram you see here. But there's a separate loop at the developer level whose each iteration is changed to the code base, like a PR that gets merged. This inner loop is incredibly important and should be well in sync with the outer loop. But excluding higher level system tests from the inner loop makes this synchronization difficult. Historically, the prevalent argument has been that high-level tests are just too difficult for developers to set up and run locally without the help of test engineers. And high-level tests are just generally slow and expensive. So these are valid arguments, but higher-level tests also have advantages. They are easier to read, for instance. And because they cover more system components, they better represent the end-user environment and are more reassuring than unit tests. So as with anything in software, using higher-level tests is often a trade-off between cost and benefits. But the commoditization of cloud compute resources and various improvements in developer tooling has reduced the cost of running higher-level tests. And in many application domains, they are no longer prohibitively expensive to be run in that developer inner loop. But why is this general industry trend less pronounced in C++ application domains? C++ applications are complex, mission-critical, and resource-intensive. So to test them and ensure that they meet our requirements, we need a large number of data sets that take time to run. So the concerns here just outweigh the benefits. But we can make a compromise to reduce these concerns to by slightly changing the problem statement from testing for correctness to testing for regression. You see, we often associate testing with verifying that our software is behaving correctly. But during development, it is enough to test that our software works as well as before. Testing for regression is easier and faster than testing for correctness because it removes the need for us to know the expected behavior of our software for each test case. So it can shift the balance towards the benefits of higher-level tests. Regression testing is not a new concept. Remember that medical software I shared? That medical software, we had this data ingestion pipeline that received DICOM images from different sources and produced this volume object that included image data and metadata to pass to higher-level system components. And at some point, we wanted to rewrite all of that code to improve robustness and efficiency. And we used regression testing for that. But our custom purpose-built regression testing system was taking a long time to run and was so complex that it required its own maintenance and support. This system worked by taking basically passing the input to the old version of our pipeline as well as the new version. And then it compared the output of the two versions of the pipeline together to see if they match each other. I always found it annoying that every time we ran this test, we had to pass the input to the old version. We knew full well that it isn't going to change. So it just felt like a waste of time and resource. One way of making tests faster is storing the output of the old system somewhere and reusing it to test at test time, and reusing it at test time so that we don't have to pay the cost of running the pipeline again. And this is not a new concept either. This method of taking a snapshot of the software and storing it on disk is called snapshot testing or characterization testing. But this method has its own challenges. For one, snapshot testing treats the system as a black box. Snapshot files only include the output, the final output of our system. So any important data that is not captured in that final output cannot be tracked with this system. For complex multi-stage software workflows, this is a major limitation, and one that makes it difficult to trace a difference to its root cause. Another limitation of snapshot testing is that the system output is stored in a snapshot file as a single entity. So there is no distinction between various data points that go into the output. And any small difference in any part of the snapshot file is enough to trigger a mismatch. Consider this receipt as an example, as a possible output of a retail checkout system. If you want to test the system with a snapshot testing, it would be tempting to store this output in a file. But the last line of the receipt includes a timestamp. So every time we run this test, the timestamp would be different, which is a source of mismatch. So we need to massage the output if we want to use this output as a snapshot file. Another limitation is that most snapshot testing libraries advocate for storing the snapshot files in the source code repository. This approach may be convenient at first, but it quickly breaks down for larger applications at a scale. Because in real-world software, the snapshot files may be too large or too many to store in our version control. And lastly, snapshot files don't preserve the type of our captured data. They often store the textual representation of our output, which means mismatches are also reported as string differences, which could be really difficult to collect insights from. So about 5 years ago, I started a side project to build a regression testing system to address the common limitations of snapshot testing. I wanted this new system to be tailored and optimized for use for developers. So it can be used continuously for testing day-to-day code changes. And I wanted it to be flexible to provide fine-grained control over what data we are capturing and how it should be compared. And I wanted it to be scalable so that it can be used by my team and other teams for testing complex real-world software. The overall architecture of that system was something like this, where a C++ library would capture values of variables and runtime of functions, and then submit all of that captured data to a server, a remote server, that handles everything from data retention, comparison, visualization, and reporting. This project was adopted by my team and gradually matured as a product to cover multiple critical workflows of our software. After another 2 years of building it over nights and weekends, I was fortunate to receive the IP rights for it. So I started showing it to software engineers outside of the company. And in March 2021, their positive feedback made me decide to leave Canon and start working on this project full-time. I founded a company, rebranded this tool to Tuka, and I started selling it to other companies. The picture you see here is me presenting Tuka at Techstars Demo Day. Now, before I start sharing about this product, I just want to make it clear that Tuka is no longer an active company and is now free and open source for anyone to use for personal and commercial use. Let's start with the server side, the Tuka server, that receives data that represent the behavior and performance of our software and remotely compares it with a previous version. Now, if the server finds any difference, it visualizes those differences in real time and reports them on this web dashboard that you see here, and reports any differences as email or a Slack notification to the subscribed stakeholders. Here's a preview of that web dashboard showing a high-level overview of how a particular software workflow has evolved over time. The left panel shows changes in the behavior, and the right panel shows changes in the performance. The server and the entire product is open source and available on GitHub under the Apache 2 license. You can self-host it anywhere that you like and use the Tuka CLI to install it locally using Docker. Or you can use the Helm chart that we provide for deploying it to a Kubernetes cluster. To describe the behavior and performance of our software, Tuka provides various SDKs and facilitates writing the test. Let's start with unit testing and just focus on this sample unit test for a software that takes the username of a student and provides basic information about them. We pass a particular username to our software and verify that the output matches the hard-coded expected values. We all know how to use unit testing. These expected values, however, are different for different inputs. So we end up with multiple sections, each verifying one test case. Now, if we wanted to test for regression, we wouldn't need to hard-code the expected values. We would just capture the actual values of our software for any given test case. And then we would pass these to the server so that it can compare those captured values against a previous trusted version. And once we remove the expected values, then the content of each section is exactly the same, except it differs in the username that we pass, the input. Now, can we go further and just say, take inspirations from property-based testing and parameterize these test cases so that it would be basically just one function instead of 3 sections? Yes, we can. And in fact, we could actually use the Tuka server to store all these test cases so that we don't even have to specify them at runtime. The SDK could just grab the list of test cases from the server and run them every version. This test framework can not only retrieve the test cases, but it can also perform other functions, such as error handling and progress reporting. Notice how removing expected values has made it so much easier to write our test and express our intention. And because our test input are decoupled from the test code, then this is all we need to write, regardless of how many test cases we want to feed our workflow under test with. This test code here is in C++, but we also offer SDKs for Python, Java, and JavaScript. Now that we know how to write our test, let's see how we can run it locally. For that, Tuka provides a command line tool that runs our test and makes it easy for us to specify which server the captured data should be submitted to. So no matter how many regression test workflows we have, all it takes to run them is one Tuka test command. And of course, we can pass additional options if you want to limit to a certain workflow or pass particular test cases. But we don't always want to run our tests locally. Obviously, with high-level tests, chances are that we are having a large number of test cases. So testing them locally just takes time. So while the CLI is convenient for and developer-friendly, Tuka provides a GitHub Actions plugin to make it easy to run the test as part of the CI. As the results are submitted to the server, they're automatically compared against the previous baseline version. And we can use the web dashboard to see the comparison results in real time. And because the remote server has access to all the captured data for other versions of our test, we can manually compare any two versions with each other and generate a summary report. This is very convenient when we are investigating the root cause of a particular difference. Given that we are capturing values of variables and runtime of functions, most of our data points are usually numbers or strings and custom objects. But the server also supports binary data and can compare and visualize differences in images and videos. Sometimes our code changes don't affect the behavior of our software, but they may negatively impact its performance. So those are regressions too, right? And they are important for us to catch during the development. Tuka has a special feature to capture performance data and visualize how they change over time. Now, what are the special features? Because unlike behavior data, performance data are usually noisy and can change across test runs. So we need to account for this noise and handle it with grace so that small differences do not cause a mismatch and fail our test. So Tuka only reports performance spikes and changes that fall outside our performance trend. Now, visualizing differences on a web dashboard is super helpful, but it involves a context switch to browse to a particular web page to see the results. And in most cases, and especially when we are running tests remotely, like CI or on a dedicated test server, we may forget to do that. So Tuka includes a reporting engine that automatically processes and compares all the results for a given version. And then once the test is fully submitted, it reports the status of the version along with high-level insights in form of email or a Slack notification. And because software development is teamwork, anyone can subscribe to any given test workflow to receive notifications about it and keep track of the changes to our software. Sometimes the outcome of a difference is that we've made a mistake. So we can go ahead and fix it after receiving that notification. But sometimes our changes are actually improvement to the existing behavior of our system. So we want to mark those differences as justified and promote our new version to the new baseline. Tuka enables that with a click of a button, of course, so that subsequent versions can be compared against our new results. So now that we saw what Tuka does, let's briefly review how it works. My hope is that this exercise could inspire you to take these concepts and apply them to your own regression testing systems. Here's the high level of Tuka, high-level architecture of Tuka. We already covered the SDKs, the CLI, and the CI plugins, all of which help us describe the behavior and performance of our software, and then pass to the Tuka server API that is written in Node.js in TypeScript. Now, the server performs data ingestion and uses third-party services for caching and storing the results. In self-hosted deployments, those third-party services are Redis for caching, MongoDB for a database, and MinIO for an object store. But when we are using Tuka at a scale and in cloud deployments, we could replace these services with their cloud services. Like we can replace Redis with Elasticache, or we could use DocumentDB instead of MongoDB. and S3 instead of min.io. The C++ SDK is designed to support a broad range of standard versions, all the way to C++ 11. This is by choice, because we want to enable refactoring all sorts of legacy code. With that same logic, Tuka supports a broad range of compilers for GCC, Clang, and MSVC. To support older standard versions, the SDK has a few dependencies listed here. So we don't offer any single header installation. Instead, you could install Tuka with CMake using fetch content. And you could also use our limited support for Conan and Bazel. Now that we learned how to write a simple test workflow, let's see what's behind the data capturing functions like Tuka check. We want capturing of the data points to be easy and developer-friendly. So these functions provide out-of-the-box support for any primitive and standard data type and are designed to be extensible to support custom user-defined types. Take this data birth, for example, which could be defined as a data object with the structure presented here. We could perfect forward the type of the given value parameter to a class template called serializer that enables template specialization for any custom type. Tuka check is not the only data capturing function. You could use log to capture any value without having it impact the comparison status of the test case. And you could use assume to make the test immediately fail because an assumption about a test input is not consistent with that assumption in a previous version. And you could use syntax trigger functions like add array element and add hit count that are easier to use, but work just like Tuka check, but they're easier to use in a for loop, for instance. Note that these functions are stateful, and they're standalone, so we can call them from anywhere within our code, including our production code. This design enables tracking important data points that may not be exposed in the output of our software or accessible from its interface. But because capturing data points in production environments is not making sense, these functions are implemented to be default no-op, unless they are called from the test framework or they're explicitly activated by the calling Tuka configure function. Tuka supports tracking the runtime of our functions as well. Here is the low-level function start time and a stop timer that enable fine-grained runtime measurement of any arbitrary execution flow. If this feels too verbose and difficult to work with, we also provide a scope timer that measures its own lifetime. So it's easy to tack it on top of compute-intensive workflows. Now, this scope variable is unique to C++ and is implemented differently in other languages. Here is the same concept implemented in Python using a with statement. The SDK also provides an add metric function to enable capturing runtime measured using different libraries or other code. I mentioned that all the data that we capture is passed to this value parameter of serializer class template. This way, we can use partial template specialization as a language feature available in C++ 11 to convert any given type to a data point variant that we know how to store and handle efficiently. We chose partial template specialization because the library can provide specializations for common types and allow users to introduce further specialization for their own user-defined types. Now, here's an example of how the library supports capturing signed integers. We add a template specialization for all non-Boolean types that are integral and signed. We implement this specialization by copying the integer value into our data point variant. Internally, this variant supports the core types listed here on the right side of the screen, where object and array are implemented in terms of map and vector of other data points. We expose objects and arrays to make it convenient and elegant for users to add a specialization for their own custom user-defined types. Here's an example of a specialization for a date object. The outcome of this design is an implementation that is as expressive as we can get with partial template specialization. But partial template specialization is not the only language feature that enables designing extension points. 2 years ago at this conference, I presented a practical overview of other approaches to creating extension points, including using concepts, ADL, and static reflection. And I tried to show how the language is evolving towards simplicity and facilitating the expression of intent. If you're interested in learning more about this subject, I hope that you find that talk useful. Let's now move on to the data submission, where when we've collected all our data points and want to submit them to the server. The top left code snippet uses the high-level test framework that automatically handles the data submission when a test case is executed. But using this framework is optional. If you're not happy with the test framework or just want to integrate Tuka with our existing test framework, we could use a lower-level API that is shown in the right side of the screen. Now, in this low-level API, data submission is handled by the Tuka post function that is implemented to serialize all the captured data and submit them as binary data to the Tuka server. We use flat buffers to perform the serialization in a way that preserves the type of our data points so that the server can compare the test results in their own original type. Here's the flat buffer schema used by Tuka, where each captured data point is represented as a result. And each performance data point is serialized into a metric. This way, we can store all the collected data for any given test case in a message object. We serialize each message first individually, then package all the serialized messages into a messages object, which is then serialized and submitted to the server. This double packaging of our data may feel excessive at first, but it enables saving network I/O on the client side, and more importantly, it leads to faster data ingestion on the server side, as the server can deserialize our top-level messages, but then defer deserializing the actual message data to its workers. Here's how the server handles an incoming submission with when a test is run as part of a CI or on a dedicated test server. In these environments, we don't care if the test is matching or not. We want to execute our test anyway. And we don't want the test to fail because a test case is not matching a previous baseline version. So it's enough for the server to just handle the data and acknowledge the receipt of the data. When the server receives the data, it deserializes the high-level messages object and stores the binary contents representing each message in a data store. And then it creates this document for each message, and then basically creates a job to defer the processing of that document to its worker threads. Now, it's at this point where the server can then acknowledge the receipt of the incoming data to the SDK so that the test framework could go ahead and move on to the next test case. Now, much of this workflow is similar when we are running the test locally. But in this case, we want to have some feedback of whether our test results are matching our baseline version or not. So the server, instead of just passing a 204 response, it waits until the test results are all processed and compared, and then creates this response accordingly afterwards. Now, last bit of the Tuka architecture is the retention policy. Remote storage of test results is obviously very convenient, but the storage has a cost. And when testing real-world data with lots and lots of data, then that cost could be noticeable. So we want a way for the server to get rid of older test results. Tuka server includes a data retention service that is configurable and helps remove older submitted data and move them to a longer-term archival solution. We also allow storing a local copy of captured data on the file system in a format that can later be used to restore that data to the server. OK, so let's now focus on how continuous regression testing can help us identify other types of regressions that we may want to identify and mitigate during the development cycle. What we'll review in this section are just a handful of examples to show the power of this method, and are by no means a comprehensive list of use cases. I mentioned earlier that the handling of performance data are slightly different, given that they're prone to noise that needs dealing with. But performance data are not the only data susceptible to noise. In fact, in real-world applications, we often want to allow a degree of flexibility and non-determinism in the data that we submit. Sometimes we can set that threshold as a minimum or maximum value. And sometimes we may want to set the threshold relative to the value of our baseline version and allow, for example, plus or minus 1% difference in that value. CppCon supports introducing these constraints as a third argument to the data capturing functions and takes them into account when comparing test results remotely. While our way of finding performance regressions does not use absolute or relative thresholds, the use cases that you'll see in the next couple of slides make extensive use of this feature. Now, the performance API that I showed you earlier is primitive. It is sufficient for tracking wall-time performance of long-running functions. But if we really care about the performance of individual functions, we need proper performance benchmarking libraries that allow executing the function millions of times, for instance, to obtain reliable performance data. These libraries have their own way of reporting their test results. In the example shown here, we're using the well-known Google benchmark, and we have a JSON report that is one of the ways that it could produce its output. It is very easy to write custom code to take in output of another tool and submit some of its data to the CppCon server. In fact, CppCon CLI already ships with a handful of plugins, one of which is for ingesting Google benchmark data. All we need to do is to install this plugin and use it to submit our performance benchmarks to the server. Now, tracking runtime performance is great, but maybe we want to track changes in compile time of our software. If any of you is using Bazel as their build system, you may already know that Bazel enables creating a build profile that details what Bazel is spending time on. Now, there's also a Bazel analyze profile command that is handy for generating textual report of that build profile. So it is incredibly easy to capture elements of this output and track changes in them. We may want to just track the overall build time or include the duration for each stage of the build. Either way, we can use CppCon plugin for Bazel or write our own plugin to track this data for any version, from any version to another. Another less common use case for regression testing is tracking the size of our binaries. One way to do this is using a tool called Bloaty that is maintained by Google. And while tracking everything in the Bloaty output is likely unnecessary, it is easy to track larger files that we care about. Or we can track the overall file size and VM size of our binary for a start. Similarly, for this case, we can write our own plugin or rely on the CppCon plugin for Bloaty that already ships with a CppCon CLI. And as a final example, CppCon can track the list of exported symbols of a shared library to make sure that changes to our library do not inadvertently remove an exported function that consumers may rely on. Here is just one example of how to obtain this list of given dilib using NM on macOS. The use cases we reviewed are just a few examples of going beyond finding behavioral regressions. I hope that they can serve as inspiration for tracking regressions in whatever metric you care about during the day-to-day development. Now, I shared a lot about CppCon, this product that has consumed almost 2 years of my life, at least the past 2 years. It's been a rewarding journey, of course, but full of ups and downs. In the 2 years of operating CppCon as a startup, we had our own fair share of success. I'm proud of the fact that we helped more than 10 companies find more than 1,000 unintended regressions during their development stage. But there's always an end to any journey and any chapter. And for CppCon, it is no different. The end for CppCon as a company was in March this year when we announced that the company is shutting down. Now, in the past 6 months, the second most frequent question I've got is what I've learned building and selling this product. And what I've learned is this, that testing is cultural. How an organization tests their software always goes back to their team culture. not the set of tools or methods that they use. Now, to better convey my point, I'd like to remind you of the broken windows theory that was first introduced in 1982 in Atlantic magazine. This theory suggests that if a window in a building is broken and is left unrepaired, then all the other windows of that building are doomed to be broken soon. And the author reasons that the unrepaired broken window is often a signal that no one cares. So breaking windows doesn't cost anything. This theory suggests that the most effective solution to larger scale bad behavior, like window breaking, is encouraging good behavior and promoting good behavior, like fixing windows. Now, I think that this theory holds true for software quality as well. In an organization where builds are slow, tests are flaky, no one cares about compiler warnings, and low-quality pull requests are landed without any conversation, the released server, the released product is also defective, more likely than not. Tools like Tuka can help, but the real champion who makes a difference is the engineer with abundant patience, perseverance, and grit that slowly takes on changing the culture and making their colleagues care. So if you're serious about improving the quality of our software, we need to embrace this culture of continuous improvement that promotes and rewards fixing broken windows. Improving software quality is a continuous process, so it also needs commitment, which is only possible if we prove the return on investment by measuring the impact of our efforts on developer productivity. And we need to educate software engineers about the best practices for building good quality software. Now, let's quickly review these topics one by one. I already outlined the importance of continuous improvement, but to drive this point home, I'd like to go back to the analogy between a complex software and a garden. You see, a good gardener is one with the habit of continuous improvement, who is always tending to their garden and plants, making sure that they have enough sunlight and water and humidity. And a bad gardener, on the other hand, is one that is totally ignorant of their plants until they start to die for one reason or another. Now, as an organization that waits until they find a serious defect in production to improve their testing practices will have the same luck as a bad gardener. To unlock the culture of continuous improvement, we also need long-term commitment and care from the software team. And the best way to earn that commitment is by collecting data and metrics to show how improving the inner loop is correlated with improving software in that developer outer loop, the software development lifecycle. Sadly, most engineering teams don't invest in measuring developer productivity enough. Now, as for education, I cannot even begin to pretend that I can cover all the best practices in just a few minutes. But I have a few thoughts, or hot takes, if you will, that are relevant to testing and refactoring. And they start with learning what to test, because testing the wrong thing is the easiest recipe for generating low quality and flaky tests. When testing becomes a chore, we give in to this temptation to create a template for it and blindly just following that template. But testing is the exercise of verifying our software system expectations, not the changes that we are making themselves. And system expectations are prone to change. So our tests are only effective if they fail from time to time. A good rule of thumb to measure whether we are testing the right thing is to think of software as an airplane. And ask ourselves, if all of our tests are passing, would we dare to board that plane? We also need to learn how to write good tests. And regardless of what type of test we write, I think a good test is one that is expressive, so that it is easy to read, and scalable, so that it is easy to run, and also extensible, so that it is easy to change. When the tests are not easy to read, run, or change, then that's a sign that our system interface is poorly designed, or that we're not using the right type of test to test this interface. Running the right type of test at the right time significantly impacts test effectiveness. Obviously, higher level tests continue to be more expensive and slower to run. but they are better and easier for some scenarios and provide more confidence than running 1,000 unit tests. And we can always leverage methods like selective test case execution to run only a subset of our test cases to get faster feedback. Now, writing tests is one thing, but I think that writing good tests require a deep understanding of the system and business requirements. And some of this understanding takes time and experience, but reading source code can help too. But reading source code is a skill by itself. It is easy to get distracted by the implementation details. A good software engineer pierces through that layer to learn the context and history of the software instead. I like to think of those of us who are working on large software systems as urban planners, trying to improve a historic city. Trying to modernize the first thing that we find by using a shiny new language feature is often wrong and hurts readability. Now, I used to live in Minnesota, which makes most people immediately think of frigid cold winters. But if you have ever lived in the Midwest, you know that the most annoying thing is actually constant road constructions. Construction zones are annoying in the world of software too. And it is so easy to end up creating a construction zone when we embark on large-scale refactoring projects. So whenever possible, we should favor small incremental refactors over big bang migrations. And my last parting thought is that adopting continuous improvement is embracing a culture of safety. Safety is essential to the company I work for, so I'd like to share some of our practices in building and testing software for autonomous driving, and show how these practices can be generalized and applied to other types of software. At Aurora, safety is a team sport. We're taking on the ambitious challenge of operating vehicles safely and autonomously in a real world that is complex, messy, and ever-changing. To ensure the safety of our product, we leverage multiple tiers of testing, some of which are listed here. We take our offline tests very seriously and fundamentally believe that they are more effective for building high-quality software than collecting vast amount of data from low-value autonomy miles. Now, because our product needs to handle a large variety of scenarios, we heavily rely on simulation tests for testing other perception and motion planning systems. If you wanted to test this scenario on the road and in the real world, we need 100 vehicle fleet operating 10 hours per day for 50 years to test one single change to our software. And we make more than 200 changes every day. So this is why simulation tests are so important. We run 6 million simulations each day to test various systems of our software in very realistic conditions without causing dangerous conditions on the road. We build custom software to simulate sensor perception with a degree of required accuracy. We build a virtual world that mimics the real environment. With a world in place, we describe how events are to take place in a time interval. Our simulator perceives this curated world and then writes a log of what it sees. These synthetic log data help our internal partners train, validate, and test perception systems at a scale. And finally, we make these simulations an essential part of the feedback loop for our machine learning models to learn how to navigate important situations that are rare and dangerous to replicate in the real world. When we observe rare but interesting events in the real world, we can use our virtual world and synthetically generate more extreme cases of those events, and then use those extreme cases as training data for our machine learning models. These multiple tiers of extensive testing help us build confidence in what we are building and let us improve our product safely and quickly. But keeping this infrastructure running requires embracing safety as a culture, an operational framework, if you will, an enabler of success, not just some business requirement. And in fact, Aurora is the only autonomous vehicle company to date to have a public safety case framework. Now, this safety case framework is obviously relevant to autonomous driving, but I like to think that any company should have a safety case framework for themselves that basically defines their culture towards safety. And then they could also publicize that safety framework. All right, so we covered a lot today. We saw how fast feedback cycles improve developer productivity and how continuous regression testing can help us change software safer and faster. But to achieve overall safety, we need to incorporate multiple tiers of testing and adopt a culture of safety and continuous improvement. I think that I want should be the thing that you take away from this talk. And with that, I'd like to thank you again for your time. And now I'm ready to take your questions.
Hey, Pejman, great talk.
Thank you.
I'll start it off. So 2 questions. Does Aurora use Tuka? And then the second question is, even if Aurora doesn't use Tuka, I assume they use some similar system. And is the tests that are done on actual hardware, not on simulation, also integrated into the CI pipeline?
Oh, great questions. Yeah, so the first question is easy for me to take. Based on my knowledge, no, Aurora is not yet using Tuka. And your second question was whether we have on-vehicle test, online test, as we call them, that would also impact our CI. Again, to my knowledge, the answer is no. We do have dev testing and online testing, and we also have this test track that we use for testing certain dangerous conditions. But they're not part of our CI. In fact, in our CI, we have extensive tests already, but we need to package some version of our product and then deploy to our trucks to test. Thank you for the question. Any other questions? Yes, please.
So I'm an embedded software engineer. So when we talk about testing performance and looking at regression there, a lot of times what I'm looking for is to do that on bare metal or on QNX or an embedded operating system of some sort. Does Tuka support those kind of use cases where I'd want to measure performance data on hardware?
I think the answer is context dependent. If I'm very honest, embedded software is so extensive and the requirements could be so difficult to satisfy that just plainly saying yes is just being naive. For certain, we have had users and we have had customers that were using Tuka in an embedded framework. But then those embedded devices had enough capacity or memory or file disk that they could at least write a file and store the file on that file system first and then move those test results later. Or they in one case they had network I/O already available, so they could just post from the server. In general, when it comes to embedded devices, I guess the performance and the requirements are just very different. So in one case, I guess to just point out is sometimes we want freestanding libraries, and we don't even want to use a standard library for that. So if that is your limit, then of course you cannot use Tuka because Tuka is using extensive use of a standard library and other libraries too.
Great. One more question for you.
Of course.
So a lot of times we end up using microservice architectures, or we're trying to test between applications that have a messaging protocol. Is Tuka, does it allow us to test both at a library level, and then could we also do that at an application level where we're actually trying to measure write messages in, write messages out?
Great. Yes, this is a great question again. Thank you. The answer is yes and yes. So you could use Tuka at a kind of like microservice level, individually testing each microservice, or you could use a suite of microservices or like basically a cluster, if you will. In that particular latter context, then you want the data that is captured to be from different sources, which is a slightly difficult sometimes because in this like free standalone function call that we had, you had to run a test framework somewhere. So oftentimes, usually running that test framework ends up being one of those pods or nodes of the cluster. And then somehow you need to propagate that message that, hey, we are running in a test mode to other pods. That is not something we support out of the box. That should be kind of custom code that you write. But yes, the library supports submitting data from multiple devices to a single source as one version.
Cool. Thank you very much.
Of course.
Yeah, I think it was on slide 22 or so. You showed an example of some regression where you printed out a receipt.
Yes,
Perfect.
This is the one.
And at the bottom of the receipt is a timestamp.
Correct.
And so this is relevant for me. I'm looking at wanting to record session information from a network stream. And I want to be able to replay that session information in an integration test. But the problem is that some of these sessions over the network have unique information that it's really hard to replay that. I'm wondering, how would you integrate that? For a timestamp like this, I would just mock the clock.
Yes.
But on a network stream, it's a lot harder to mock each individual component. So I'm wondering, how would you solve that?
Great question. I guess there is no silver bullet. Difficult problems usually often ends up with difficult solutions. In this case, I think with custom code is the only way. Tuka itself is offering this primitive suite of data capturing functions to enable extensibility and use in different application domains. But it doesn't have any special purpose-built facility in it to basically deal with non-determinism of, say, network I/O or things like that. In general, non-determinism is a big deal. It's very difficult to solve. I don't envy people who need to test those type of systems. But in general, I think this slide, the purpose was to show the limitation of a snapshot testing. And I think you could make the same argument that snapshot testing is no good solution for that context either. So I'm sorry for not having a good, better answer for you.
No, I think that's good. Thank you.
Yeah, of course. All right, any other questions?
All right, so if there's no one else, I'll have one
Yes,
more.
please.
So does Tuka support having local runners? Say, for example, right, I've got my CI pipeline and there's a lot of things I want to test, but I want to actually deploy that to a bespoke piece of hardware, run those things, and then get that data, those snapshots back up?
I'm so happy to be able to say yes to this because it really was difficult to implement. But yes, we do. And in fact, the reason why we have the JFrog logo here is to indicate that you could deploy your artifact or whatever somewhere as part of your CI and then decide to run the test on a separate test server. This is actually a very common case when we are dealing with large software, complex software, because running Tuka as part of the CI is kind of like subscribing with the pain of long-running tests being as part of the CI. So more often than not, you want to have a dedicated test server where the test would run there, but then they should be able to know when to run. So for that, we offer two approaches. One, the Tuka CLI has a Tuka run command that could basically point to this JFrog artifactory repository that you have. And anytime a repository gets a new artifact, it could just know that it should install it and run it. But then also we have the ability to run the command on a scheduled basis. So you could say, I want them to run every night instead. In that case, the Tuka run command would just pick the latest available artifact from the artifactory, and if it has not run that yet, it would run it. Great, yes. One last question, because we have only 30 seconds.
Yeah, toward the end of your talk, you talked about simulation tests versus hardware-in-the-loop tests. I was wondering if you could talk more about your thought process when you have an aspect of the system. How do you decide, is it worth a hardware-in-the-loop test? If you do a hardware-in-the-loop test, how do you target it? What's your process there?
I feel unqualified to answer this one. I think, again, this is context dependent. In a lot of cases, We have hardware in the loop, not because we cannot run simulation, but because it's something different that we want to test that we cannot do with simulation. So in general, I think hardware in the loop is just a way of testing something that is the most effective way that we know of.
Yeah, thank you.
Yeah, of course. All right, and with that, thank you again for being here. I hope that you found this insightful.